What's going on, everyone? It's Mr. Nickel here. We're going to be talking about 6.2 in this video. We're going to be talking about exponential growth and decay functions and the differences between them. And then our goals here are we're going to use and identify exponential growth and decay functions. And then we are also going to be able to solve real-life problems involving those functions. Okay, so once you have your title in your notebook as well as the learning objectives, I'd like you to try this warm-up for me. There are a total of 128 teams at the start of a citywide 3-on-3 basketball tournament. Half of the teams are eliminated after each round. Write and solve an exponential equation to determine after which round there are 16 teams left. We should start by trying to put the information that we just found into a table. We've seen exponential functions in tables quite often so far in the class. So we need inputs, we need outputs. Well, after each round, we know the total number of teams change. So after each round, how many teams were there after the 0th round, meaning when we started? 128. How about after the first round? There were 64. And that we know that because there were half of the teams are eliminated. So we're multiplying each time by 1/2 or by 0.5. Either way. So after the second round, we would be at 32. After the third, we'd be at 16. After the fourth, we'd be at 8, and then 4, and then 2, and then finally, we would have our winner. Okay, so we've created our table. It's easier to see our information, and it wants us to write and solve an exponential equation to determine after which round there are 16 teams left. Well, we see how many teams, there are 16 teams left after the third round, so we can answer that question using the table. Another reason the tables are nice. But to answer the first part of this, to write it in exponential equation form, we need the equation itself, y equals a times b plus x. A is the y-intercept, and in this example we are given that. A is 128. Whenever x is 0, our y-intercept is whatever y is. And we know what b is, because b is our common ratio, what they are changing by, and we know that they're multiplying by 1/2, or 0.5. I'm going to stick with the fraction, which is 1/2, and then we just combine these three pieces of information. We write y is equal to 128 times 1/2 to the x power. After which round do we have 16 teams left? That would have been the third round. So y is equal to 128 times 1/2 to the third power, because we believe it would be at the third round. So y is equal to 128 times 1/8, and therefore y would be equal to 16. In this slide, I've given you a core concept from your textbook that discusses exponential growth functions. Be sure that you're gluing in the correct one that says growth. The decay one looks very similar. Write in your key term, exponential growth function. And then I want you to highlight the fact that exponential growth functions increase by the same factor over equal intervals of time. Looking at the equation itself that I have in this core concept, y is still the same, but x has disappeared and instead turned into t. So we're going to be talking about measuring time. So our input will always be the time. And then our b, the parent function and the common ratio, that changed to something looking like 1 plus r. 1 being 100% of something happening, and then plus whatever the growth rate is. And we'll talk more about that in an example here soon. Example 1, we're going to write exponential growth functions. Please write that in as your on the left-hand side of your Cornell style notes. Let's read the example here. It says, the inaugural attendance of an annual music festival is 150,000 people. That's a lot of people. The attendance, y, increases by 8% each year. Okay, so we see some big stuff in here. We see the typical number of guests that went to this festival. We see that the attendance we're going to denote with the letter y. And then we know that we're increasing our population to this music festival by 8%. So this is going to be a growth function. So you should be visualizing that this, if we are graphing, this is going to be growing. Part A wants us to write an exponential growth function that represents the attendance after t years. So in order to do this, we need to remember what that function looks like. We just got this in from our core concept. It looks like a times 1 plus r to the t power. So we need to find our components. Y and t will stay the same because t is our input and y will be our output. The letters we need to figure out are a, where we're starting, and r, what we're growing by. R is our growth factor, a is the starting point, he's our y-intercept. So where do we start at? What would a be equal to in this example? Well, a, in this example, we know the music festival has 150,000 people that attend. So I'm going to highlight this. We have 150,000 people for attendance. So A would be equal to 150,000. That's how many people we're starting with. R is whatever we're growing by. And so I see up here that it says the attendance Y increases by 8% each year. Okay, so we have our growth factor here. Let's highlight this piece. It increases by 8%. But the problem with 8%, we'll write this in here. The problem with 8% is we can't use percentages in mathematics, in calculators, or any type of calculations in general. So we needed to turn 8% into a decimal, and we do that by putting it 2 decimal places back, 0.08. Awesome. Now that we've got those components, we can put this into the equations form. It looks like y is equal to 150,000 times 1 plus 0.08 to the t power. And so we'll simplify this a little bit here. 150,000 stays the same, but we can add 1 plus 0.08. That turns into 1.08. And so if nothing ever changed, we would just multiply it by 1, and that would never change. We'd always have 150,000 people that goes to this festival. But if we add 8% every single year, then we're going to multiply by 100.8%. So they're going to be growing by multiplying the typical attendance by whatever our growth is. Okay, and so we can answer our question with this function. It says how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. Okay, well, for part B, we know t must equal 5 because we're in the 5th year. And so let's just plug this guy in now to our function that we wrote. We have y is equal to 150,000 times 1.08 to the, not t power, but to the 5th power now. When we type this in our calculator, we get y is equal to 220,399.21152. Back up at the question up here, it says how many people in the 5th year? Well, we found that, but we can't have decimals for people. And it also asks us to round our answer to the nearest 1,000. Okay, so this is the ones, the tens, the hundreds. This is the thousands. So to round to this number, we look to the number before. Is that number bigger than 5? No. 3 is not bigger than 5. Therefore, we will round down, and we have 220,000 people after 5 years will attend this music festival. Please try the following on your own. After you've paused and worked on this video, we would get our function that would look like y equals a in this example, which is 80,000 people that starts at this music festival. We would multiply that by 1.06 to the tth power. That would be our exponential growth function. Then how many people will attend after the 5th year? That would be when t is equal to 5. And so very similarly, we would have 80,000 times 1.06 to the not t power, but to the 5th power. And so y would be equal to, after you type that in on a calculator, 107,058. And then you get some decimal, 0.46, and it keeps going. But we're rounding this to the nearest 1,000. And so we would again look at this number. Okay, well, 0 is for sure less than 5, and so we would round down again. This would be y equals 107,000 people that attended this music festival. We've glued in a core concept about growth functions. Now we're going to glue in a core concept about decay functions. Okay, so make sure you have your highlighter out. Make sure you write in our core concept and our key term. This key term is exponential decay function. And then this time I want you to highlight exponential decay functions decrease by the same factor over equal intervals of time. Just be vigilant. The difference here in our equation, they are very, very, very similar. The only difference is we're not going to be adding to 1 inside of our parent function. We're going to be subtracting by 1. Hence why we go low. Our graph is going to be dropping. Distinguishing between exponential growth and decay functions, that'll be the focus of example 2. So exponential growth versus exponential decay. We've got 2 tables. Your job is to determine if they're growing, decaying, or potentially neither. The first thing you do with every exponential table is see how your x's are changing, and all of these are increasing by 1. Then how are your y's changing? In this example, they're getting smaller. And if you need to think about how 270 multiplies to become 90, you can always work backwards. So instead of trying to multiply by something to get 90, you can take 90 and divide 270, and that will give us 0.333, and it just keeps going on. And that's another way of saying multiplying by 1/3. And so you can see that these are all multiplying by 1/3. And even in decimal form, you understand that 0.33 is smaller than 1. And so this function is an exponential decay function. And the reason that this is an exponential decay function is because our common ratio is smaller than 1. Since b, which is the number that they're multiplying by, is less than 1. So in part B, we see our table has x values that are increasing by 1. So it's increasing constantly. How are our x's, or excuse me, our y's changing? Well, to get from 5 to 10, we can see that that's multiplying by 2. And you can do the same strategy. If you need to know how to get from one number in the table to the next, you can start backwards. You can start with 20 and divide by 10, and that will give you 2. And so we're multiplying by 2, multiplying by 2, and therefore we have an exponential growth function. Exponential growth function, since b is greater than 1. And had we not found a b at all, had it not been multiplying by the same number at all, then we wouldn't have found an exponential function at all. We would have said neither. Try these on your own. On x table in the first table, we see we're increasing by 2 constantly, so that's okay. But we don't see multiplying to get from each value. Instead we see adding by 7. Adding by 7, adding by 7. So we actually don't have any exponential function here. We have a linear function. Anytime you're adding or subtracting constantly, you're always having a linear function. An exponential is one that multiplies. So in our second table over here, we see we're adding by 1 constantly in the x values, so we're okay in that front. And then our y values, we can see that we're getting smaller. But again, to think, how do we get to 16 from 64? Well, take 16 and divide it by 64. You're going to get 0.25. So we can say multiplying by 0.25, or we can also say multiplying by by 1/4, because 0.25 is the same thing as 1/4. Okay, so this is an exponential decay function. Example 3, we again look at determining growth versus decay functions. This time we're not looking at tables, we're instead looking at equations. And so it's important to know the 2 equations, the growth and the decay function equations. They look like this. I'm just going to write them out really quickly. Growth looked like y equals a times 1 plus r to the t, and the decay function looked very similar. The only difference was that r wasn't being added by 1, it was being subtracted from 1. Okay, so looking at our two examples, looking at a, does it look like the parentheses got bigger than 1? Well, of course, we added something in here, yeah? So for part A, we would say growth, because that number inside is bigger than 1. We had to have added something. And it doesn't only want us to identify if it's an exponential growth, but also to identify the percent rate of change. And in order to do that, we need to know what r is. So what did we change from 1 in here? We must have added 0.07. So r would be equal to 0.07, and therefore our r would be equal to 7%. It was a 7% growth. On part B over here, on the other hand, our number inside of the parentheses definitely got smaller than 1. We had to have taken something away. And so for part B, we'll say decay. But we also need to know what r is. And r, we had to have gone from 1 to get to 0.98. So you can take 1 and subtract 0.98. And that would give you 0.02. And so therefore r would be equal to 2%. That will be the end of our 6.2 notes. You may dispose of any of the other cutout notes that I had printed out prematurely. Time to work on our practice problems from 6.1 if you still have not finished those. Those will be due next class. You can work on 6.2's practice problems if you finished with 6.1, or you just would like to practice on some of the problems we just tried in this section's notes. You can work on the pre-class video from 6.1 maybe if you haven't turned it in by now. And then I just want you to be all aware that we have our first check for understanding next class. So please make sure you're ready to go. Those problems will be based off of the 6.1 practice problems. All right, I'll see you next class.